I think today, for the most part, it's going to be real important that you're doing your very best to stay awake, because it's going to be a lot of me talking and hopefully you listening and thinking at the same time. So work real hard at thinking. Jot down some notes that hopefully make sense to you as far as giving you insight into what I'm saying. All right? But you're going to want to work real hard at paying your very best attention and think with me. Okay, there's a lot of slides to go through, including a lot of slides with different kinds of graphs. Lecture A, excuse me, today, I'm going to do a little bit more with normal curves, including a harder problem where you've got to find the area between two numbers. Focusing on using a table. Now you can use your calculator, but I would encourage you, if you know how to do normal curves with your calculator, to also practice using a table. Okay? It's a good thing to be able to do it both ways. If you don't know how to do it with the calculator, you always can use a table. Table A. We'll talk about showing work. If we have time in Lecture A, we're going to talk about scatterplots. Lecture B, we're going to get into more on scatterplots and something called correlation and regression. Very briefly, let's go over what I talked about with density curves last time to warm us up toward the normal curve. Normal curve is not the only kind of density curve. Okay, it's the most common kind that we'll use in this class, but it's certainly not the only kind of density curve. We talked about a uniform distribution last time and a triangular one. That triangular one, by the way, is not the only kind of triangular one. That one that I drew in class last time was symmetric. Okay, essentially it's an isosceles triangle. But you can certainly have distributions that are not symmetric, like that, and are still triangular in shape. Okay, it depends on what the data are, what the data look like. Okay, so that's not the only kind of triangular distribution. There are lots of other kinds of distributions. They don't have to be triangles or rectangles or normal curves. For example, you could have a distribution that looks like a trapezoid like that. You could have a curved distribution that looks like this, skewed. It is important that they're always on or above the axis, and it's also important that the total area underneath them is equal to 1. You want to scale things that are always equal to 1, which can also be thought of as 100%. And the idea is that they model what's going on with random sampling. On the spreadsheet, the point was to use this built-in function, rand, to do the random sampling. Okay? That's simulation. It's not actual data that you would obtain from some experiment. It's simulated data. Rand, again, what it does is it produces a random number between 0 and 1 in a uniform way. Essentially, every number to a certain number of digits is equally likely to occur. When you multiply it by 10, that just scales it up to be a random number between 0 and 10. And basically what we saw when we applied this equals 10 times rand over and over and over again was that the histogram for the data that we got, the simulated data, was roughly similar all the time. These bars are not the same heights because you shouldn't expect the outcomes to be exactly the same because of random variation. However, they're all approximately the same height, and as you continue doing the simulation, you got similar kinds of graphs. And it was approximated by this uniform distribution, it's a horizontal line, representing the idealized situation where all the bars do have the same height. Okay, if you want to imagine that, imagine bars underneath this. If you do other things like 5 times rand plus 5 times rand, you can get different distributions. The idea here is you're applying rand twice, evidently, though I don't know for sure how spreadsheets work, independently of each other. For example, the first rand might produce 0.1, and the second might produce 0.5. 5 times 0.1 is 0.5, and 5 times 0.5 is 2.5. Add those together, 0.5 plus 2.5, you get 3 for the answer. That would be the random outcome of that particular thing if the first one was 0.1 and the second one was 0.5. The histogram ends up being different. Okay? It has a symmetric kind of look to it for one thing. You might say, well, I can approximate that with a bell shape. But it turns out that the triangular distribution is better for this particular one. Okay, that turns out to be a more accurate model. Why do you get numbers that are close to 5 more often than small numbers and big numbers? Here's the intuition. if the first rand happens to produce a real small number like 0.1 or 0.2, the second one, well, that's not necessarily likely to also produce a number that's 0.1 or 0.2. Okay? It's probably going to produce 0.3 or above. That's more likely, even if the first one produces 0.1 or 0.2. Because of that, because they're not both likely to be real small, their sum is likely to be at least moderately sized or big. Okay? On the flip side, if the first one ends up being a big number like 0.8 or 0.9, then again, the second one is not likely to be something like that. It's likely to be smaller. In fact, I think in a sense, the fact that this is triangular is proof that these two rands are producing different numbers when you apply them twice like that. In your electronic homework, you should have gotten distributions that were more like this, when you were using equals 10 times rand times rand. Smaller numbers were more likely. Why? Well, essentially, intuitively, it's because when you multiply two numbers between 0 and 1, you get a smaller number than both. That's the intuition. For example, 0.5 times 0.5 is 0.25. 0.5 times 0.6 is 0.3. That's the intuition for why smaller numbers are more common when you do this. And by the way, that's not equivalent, evidently, to doing this, because that would be taking rand once and squaring it. Whereas here, again, evidently, it's applying rand twice and getting two different numbers. Okay? The triangular distribution, that's what models 5 rand plus 5 rand. Here's the key to using these distributions. This is one of the most important things for the whole semester. The key to using these is that when you want to approximate a percentage of data values in a certain range with a given density curve, whether it's uniform, triangular, trapezoidal, or normal, or some skewed distribution, you calculate the corresponding area under the curve. The area between the two values you're thinking about and under the curve. That's the area you calculate. If it's a simple triangular distribution, uniform, or trapezoid distribution, you can find areas by using trigonometry or using geometry. For example, the area of a trapezoid like that is the base times the average of the two heights. Or you can think of it as a rectangle and a triangle and add those two areas. When you've got a normal curve, it's not so easy. You can try to eyeball the area approximately, but you need technology or the table to help you find the areas under the normal curve. Because it's curved. No straight line segments in its graph. That's a really key thing. You calculate the corresponding area under the curve. I think I'm going to skip over this slide for today, and we'll get on to doing the problem here in a minute. I do want to emphasize that, once again, you can have skewed distributions, skewed continuous distributions, like the one I drew on the board, or like these two. This one's called an exponential distribution. Okay, it's sometimes used to model things like failure times. For example, I've never actually done this experiment, I've heard that battery lifetimes under stressful conditions where the battery is being used tend to follow an exponential distribution. How long does it take for the battery to fail? Is the question. Essentially the fact, there's supposed to be a horizontal axis shown here, I'm not sure why it's not. Essentially the fact that the bulk of the mass, so to speak, under the curve is in low values means that most batteries fail in lower values. That's more typical. Where on the other hand, there's less mass way over here, but there is some mass, it's a skewed distribution. There are some batteries that last a real long time, much longer than you would expect. It's a right-skewed distribution, therefore, because the mean is more sensitive to outliers than the median is, the mean is to the right of the median. We haven't talked about means and medians for skewed distribution. We talked about it for data. This is not data, it's modeling data. The mean is the balance point if the area under the graph was made of like a thin sheet of metal or something, and the horizontal axis was a teeter-totter. The mean is the balance point, just like for data. The median is the halfway point in terms of area. Half the area is to the left of the median, and half the area is to the right of the median for density curves. Here's another skewed distribution, right squared. It's called the chi-squared distribution. I'm not going to get into the details of this, but it's useful for analysis of what are called two-way tables. We'll get to that in chapter 9. It's also right-skewed, and therefore, again, the mean is bigger than the median. With left-skewed, it switches. The mean is less than the median in that case. We're not going to talk about how to find areas under these right now. Here's a picture that, once again, emphasizes that the mean is the balance point. You can actually imagine the area under the graph as being made of like a thin sheet of metal. It's got some mass to it, and you're putting it on a teeter-totter, a seesaw. You got to put the fulcrum at the mean right there to make it balance. If it's too far to the right, then it tips over this way, and if it's too far to the left, it tips over that way. Okay? So the main usefulness of that is just to get an intuitive feel for approximately where the mean would be. Okay, here was our main example from last time. Let's modify this problem a little bit to do another calculation problem on the board. Here's something where you might want to take some notes. In fact, I would highly, highly encourage you to take notes. I'm going to focus on how to show your work for this kind of thing. Let's do a new question. What percent of the scores for the ACT, that's what most of you take, I think, math test, are between, the mean there for the ACT is 18 and the standard deviation of 6. Let's say between 16 and 26. There is an issue here, especially with the ACT. Is this inclusive or not? Should 16 and 26 be included in the calculation? Or is it exclusive? Should they be excluded? Meaning really between 17 and 25. I'm going to leave it vague here. Okay, these are just approximations anyway. I'm not going to worry about it right now. Maybe later in the semester we'll worry about whether it's inclusive or exclusive. It's less of an issue with the SAT because the range of scores is so much bigger with the SAT. But with the ACT, you've got this smaller range of scores possibilities. So it is an issue, but we're not going to worry about it right now. It's an approximation anyway. You should draw a picture in all future homework problems where you're doing this kind of thing. And it won't just be chapter 1, it will also be later chapters where you're doing this kind of thing. Of a normal curve as part of your work. You can draw the original normal curve that is centered on 18. That's the mean, mu, of this density curve. We're using Greek letters for means and standard deviations of density curves to distinguish it from means and standard deviations of data, where we use x bar and s. Standard deviation, sigma, lowercase sigma is 6, so this is 24 here. Notice that this is an inflection point right there. The graph is changing from a frown to part of a smile on either side of the inflection points. This distance right here is also 6. And therefore, this is 12 right there. Shade the appropriate area. The area is the answer. The area is your approximation for the answer, for the percent of scores that are between 16 and 26. Try to get it approximately right. 16 is closer to 18 than it is to 12. Right about here. There's 16. 26 is to the right of 24, right about there. The answer to the question is this area that I'm shading right there, under the curve between 16 and 26. Again, not worrying about the fact that these ACT scores are really discrete rather than continuous. You can't get a score of 25.2. Not worrying about that. We're using this as a model to get an approximation. This area is our approximation for the answer. So you should shade this area. You also could shade another area under a different normal curve. Do you have to do both? No, one is sufficient. This is going to be a standard normal curve. Standard normal curve. That's what the table is all about. This one's centered on 0 and has a standard deviation of 1. So that's 1 there, and this is negative 1 there. The area you're going to shade under this one is going to be the corresponding area that you get by essentially applying that z-score formula. Z equals x minus mu over sigma. Apply it to both 16 and 24. When x is 16, what is z? Z is 16 minus 18 over 6. Negative 2 over 6 is negative 1/3, is approximately negative 0.33. What does that tell you? It tells you a score of 16 is 1/3 of a standard deviation below the mean. That's what the z-score formula is doing. It's counting how many standard deviations above or below the mean you are. When the number is below the mean, you get a negative number, the z-score. We're 1/3 of a standard deviation below the mean. We're out of room over there. Coming back over here, x equals 26. That's going to correspond to a z-score of 26 minus 18 over 6. That'll be 8/6, which is 4/3, which is 1.3 repeating, which is approximately 1.33. Those are the numbers you would label here. This is negative 0.33, and this is positive 1.33. The area you want to shade under this one is there. And these areas are the same. These areas are the same. Now, if you drew these on the same scale, this one's more spread out than that one is. And so actually the peak would be lower and it would be more like this with this one because the standard deviation is bigger. So to make the total area equal to 1, it would have to be lower than this one is. But we're not really worrying about that. These areas are the same. Let's use the table. Table A, you can go to the front of your book if you can see it better there. Oh, it seems like somebody took the marker here. Anybody happen to have a whiteboard marker on you? That would be nice. You do? Okay, great. Just throw it to me. Oh, I dropped it, forever recorded on YouTube. Okay. How to use the table. There's two z's this time. The one on the right, well, that was 1.33, so look for 1.3 and then a 0.03 for the 100th spot. Zoom in with the camera there. See both of those? You see those in your table? This row and this column meet, it looks like right there. Kind of blurry actually on the screen. 0.9082 is what you should see. What does that tell you? That tells you the area under the standard normal curve to the left. Notice how this is shaded up here. To the left of 1.33, all the way forever, to minus infinity, is 0.9082 approximately. We also need the other one, negative 0.33, negative 1/3. Go back over here where you see a negative sign. Negative 0.3, look at the 100th spot, 3. Where do those meet? Right here it looks like. A little blurry on the screen, that's 0.3707 is what you should see in your book. That's the area to the left of negative 0.33 forever. You go forever. Now you might say, well, you can't get negative ACT scores, so how can you go forever? It's just a model. And the area to the left of, for example, 2 standard deviations below the mean, or even 3, is so small that it's negligible. You don't really worry about it. So, what should we do to use those numbers to find the answer? Say it louder.
Subtract the 0.9 from the 0.3.
Yeah, subtract them. The answer for the percentage as a decimal is 0.9082, right? 0.9082 minus 0.3707. Oh, I'll try to do that in my head. 0.5375. Somebody double check that?
Yeah.
Okay. Probably good to round that to the nearest whole percentage. About 54%. This is a model anyway, it's imperfect. But that's what we'll go with. 54% is the approximate percentage of ACT math scores that are between 16 and 26. If it were inclusive, including 16 and 26, it might be a little bit bigger than this. If it were exclusive, it's probably smaller. I'm not saying whether it's inclusive or exclusive right now because we're not going to worry about that complication. Keep things simple. Okay? Can I clarify anything there? So draw your picture. Make sure you write your answer and circle it. Make sure, this is real important, keep your Z's distinct from your areas. I often see many people, for example, write Z is 1.33, then they look in the table and they write, that equals 0.9082. No, it doesn't. Don't write that. Okay? Bad, bad, bad. They're not equal. They correspond to each other. You can maybe put an arrow, 0.9082, but don't put an equal sign. And I may take off like a small amount of points for doing that kind of thing.
So as far as like the sketches go, it doesn't matter which one we do, right?
You can do either one,
Okay.
yeah. You should show your Z calculation, you should show your final calculation, in this case it's subtraction, and you should circle your answer. In chapter 4, we'll start to use what's called probability notation as well. We'll put some variables in here, inside some function arguments. Essentially, we'll have a P standing for probability, and we'll put some things inside some parentheses. But we don't want that complication right now. Can I clarify anything else? All right, let's keep going here. No, not quiz time yet. We're making good time, I think. Okay, good time. We're going to move on to chapter 2, okay, which you should have skimmed beforehand, class. That's ideal to skim it ahead of time. You'll get much more out of it if you do. Chapter 2 is about what's called bivariate data and scatterplots and things you can do with them. I suppose I should probably erase my marks here. And you can get your mark back. Well, I'll keep it for the moment, but don't forget it. Just in case I want it again. Okay. It's probably worth writing this down, especially if you don't bother downloading the PowerPoints. Sometimes individuals will have more than one variable associated with them. Okay, for example, if you're all my individuals, you have lots of variables associated with you. What's your sex, male or female? What's your age? What's your height? What's your weight? What's your GPA? Where do you live? Some of those variables are quantitative, some are categorical. Okay? Lots of other different variables you can think of. Anytime you have at least two variables, and we'll focus on two, and we group them together, with two variable values for each individual, we call the resulting data set bivariate data for two variables. If both variables are quantitative, we can represent the bivariate data as ordered pairs like this. And I don't know why this is not ... Okay, it was on my computer. I have a Mac, that's a PC. That's my guess why it did something weird here. This was supposed to be a ... I'm glad I had the markers. Okay? Don't draw those funny arrows there. Okay, draw ... Those are ordered pairs. X1 comma Y1. You know, maybe the first number is 120, the second number is 105. Put a comma between them, put them in parentheses, etc. What do you think of when you see those kinds of things, those ordered pairs? Do you have anything that you imagine in your mind's eye right away?
Graph.
You should imagine graphs. These are points. More technically, they're Cartesian coordinates for points. These n pairs are typically thought of as coordinates for n points in the plane. Now that dot's kind of low. Okay, technically speaking, they're called Cartesian or rectangular coordinate plane, and these are rectangular coordinates. Because of this, we can graph them in the usual way that you're used to. No polar coordinates here, okay? The usual kind of way. Such a plot is called a scatterplot. Okay, before I go into the next slide, I want you to realize that these scatterplots are not your typical kinds of plots that you encounter in, for example, algebra and pre-calculus, or future calculus. It's not the typical kind of plot where you plot some points and you connect the dots. It's not that kind of thing. It's data. And data typically is messier than pre-calculus kinds of graphs. All right, it's not a curve. It's just a bunch of points, and they're scattered, and that's why we call it a scatter plot. For example, like that picture. Yeah, I do need this one. And, oh, yes, by the way, I made myself more space here today. I don't have to go around. I should have thought of that earlier. It's a bunch of points scattered all over the place. Now, data always comes in context. And I'm not describing the context in words here, but you should try to gain some skill at guessing the context based on the labeling of the graph, which is why it's real important to label graphs. The title of the graph says calorie and life expectancy in 134 countries. The horizontal axis says daily calories as a percent of recommended. The vertical axis says life expectancy in years. Do you think these points are referring to individual people, or do you not? That's my first question. Based on the labeling. What do you think, Tim?
No.
No, and you're right.
Probably country.
Probably countries. The individuals, by this labeling, evidently, it's 134 points there. I haven't bothered counting them. 134 points there. Evidently, each point represents one country. Which is probably the U.S. My guess is the U.S. is probably that one, right? We eat the most, and we live fairly long. U.S.? Question mark? Okay. Do we really eat the most? I don't know. Not a bad guess, I think. U.S., I'll put a question mark. I'll hedge my bets there. What is this telling you? What are the coordinates of this point? Go vertically down to the horizontal axis to estimate the x-coordinate. Let's just guess. The scale is not real great. And this is not the origin over here, by the way, either, because that's 76. Maybe let's say 165, just making up a number. We eat, all of us, on average, 165% of the recommended calories. Yikes. What about the second coordinate? Go horizontally over to the vertical axis. What's our life expectancy? Again, this is not the origin there. That's 41, 79, 72 maybe? Rough guess. Actually, I think that's pretty low. That might be fairly accurate for men. It's not accurate for women. I think women is higher. Maybe even men is a higher life expectancy these days. So taking essentially everybody in the country, you're saying on average, people eat 165% of their recommended calories, and 72 years old is the life expectancy. Maybe this is the US over there, one of those two. Okay, I don't know. All right? So imagine doing that for everyone, and you get the scatter plot. What is the scatter plot telling you? Is it talking? This is real important. You're going to have lots of questions, and you've already had some where you have to do critical thinking. You have to think carefully about what the math and graphs are telling you. What does it mean? Any ideas? It's a big cloud of data, kind of scattered. Is there a pattern to it, and is that pattern telling you anything?
The more, in general, the more calories consumed, the longer the life expectancy.
Yeah, in general, for these countries, the higher the average calories that you take in, the bigger the life expectancy is. If you split this graph into 4 quadrants, not the ordinary quadrants, but the following 4 quadrants, you're going to happen to have a red marker. The following 4 quadrants, say right about there and right about here. This quadrant, that, and that. It's not the ordinary quadrants. This number right here is my estimate for x bar. Let's just pretend it is x bar. The mean of the calorie intakes for every country put together. And this number over here, let's say that's the y bar, the average of the life expectancies of all 134 countries. You've got these 4 quadrants. Most of the points are in the upper right and the lower left. Very few, relatively speaking, are upper left and lower right. When that happens, that's an upward association, a positive association. There's a positive trend. By positive, I mean the trend here is like my arm, and it has a positive slope. It also means that higher than average values for x typically correspond to higher than average values for y, and lower than average values for x correspond to lower than average values for y, because most of the points are in the upper right and lower left. Again, that's called a positive association, and there's a positive trend to it. If you follow the trend, a line, say, that line would have a positive slope. You certainly can have scatter plots with a negative trend, where most of the points are in the upper left and lower right. There would be a negative trend, a negative association. Okay? So that's our first mini lesson about scatter plots. We're going to talk about it more after break, but it is time for break.